What is the central question for the artificial life, A-life community according to the paper?
The central question for the artificial life, A-life community according to the paper is, how do self-replicators arise and take over environments on computational substrates formed atop various programming languages? The paper explores the emergence of self-replicators in different computational substrates, such as BrainFuck, 4th, Z80 and 8080 CPUs, and SUBLEQ, to understand the dynamics of self-replication and the transition from a pre-life period to one abundant with self-replicators. The experiments conducted in the paper focus on studying how self-replicators emerge mostly due to self-modification, with or without background mutation rates, in various computational environments. The paper aims to investigate the spontaneous emergence of self-replicators in computational systems and explore the potential for new forms of life and complex, evolving behavior on computational substrates.
How does the proposed method of self-replicators emerging on computational substrates differ from traditional approaches in the field of origins of life and A-life research?
The proposed method of self-replicators emerging on computational substrates differs from traditional approaches in the field of origins of life, OOL, and artificial life, A-life, research in several key ways. Firstly, the traditional approaches in OOL and A-life research often focus on studying life after self-replicators are already abundant, while the proposed method explores the emergence of self-replicators from a pre-life period. This shift in focus allows for a deeper understanding of how self-replicators can arise spontaneously in computational systems. Secondly, the proposed method involves initializing random programs in environments without explicit fitness landscapes, where self-replicators emerge primarily through self-modification and interactions among different programs. This contrasts with traditional approaches that may involve handcrafted self-replicators or specific fitness functions to guide the evolution of lifelike behaviors. Additionally, the proposed method explores a variety of computational substrates, such as BrainFuck, 4th, Z80 and 8080 CPUs, and SUBLEQ-like languages, to observe the emergence of self-replicators. This diverse range of substrates allows for a broader exploration of the conditions under which self-replicators can arise, compared to the more focused approaches in traditional OOL and A-life research. Moreover, the proposed method introduces novel complexity metrics like high-order entropy to analyze the evolution of self-replicators, providing a new perspective on the emergence of complexity in computational systems. This analytical approach differs from traditional methods that may rely more on mathematical models and simulations to study the dynamics of self-replicators. Overall, the proposed method offers a fresh perspective on understanding the origins of life and the emergence of self-replicators on computational substrates, highlighting the importance of self-modification, interactions among programs, and the exploration of diverse computational languages and environments in studying the fundamental principles of life emergence.
Illustrate the step-by-step process of self-replicators arising in a 2D environment as described in the paper.
In the 2D environment described in the paper, a soup containing BFF programs arranged in a grid is set up. At each epoch, programs interact with their neighbors by selecting random pairs and executing the resulting code. The programs overwrite each other based on the interactions. Self-replicators emerge in this environment, starting from random programs. Initially, the grid contains random noise, but eventually, a self-replicator arises. The self-replicator quickly takes over the space, replicating itself across the grid. As the simulation progresses, the self-replicator dominates the environment, competing with other programs. The self-replicator evolves and persists, showcasing complex behaviors. The emergence of self-replicators in the 2D environment demonstrates how these replicators can arise and propagate in a spatially constrained setting, leading to competition and coexistence among different replicator variations.
What is the significance of the
significance of the primordial soup simulations lies in demonstrating how self-replicators can spontaneously emerge in computational substrates without the need for handcrafted initial replicators. This experiment showcases the ability of programs to self-modify and interact with each other, leading to the rise of self-replicating entities. The simulations provide insights into the dynamics of self-replicators in different dimensionalities, such as 0D and 2D environments, and highlight the competition and cooperation among self-replicators within the computational substrates. Additionally, the experiment with subleq serves as a counterexample, showing that certain languages may require longer initial self-replicators to arise spontaneously. This experiment underscores the importance of the length of self-replicators in determining their likelihood of emergence. Overall, the primordial soup simulations contribute to understanding how lifelike behaviors can evolve from simple computational systems, paving the way for further exploration into the emergence and evolution of complexity in artificial life forms.
What is the theoretical basis for the complexity metric introduced in the paper, and how is it computed in practice?
The theoretical basis for the complexity metric introduced in the paper is called high-order entropy. It is defined as the difference between the Shannon entropy and the normalized Kolmogorov complexity of a string. The metric aims to capture the amount of information that arises from relations between different characters in the string, rather than from random noise. In practice, the high-order entropy is computed by estimating the Kolmogorov complexity of a string, which is uncomputable. To overcome this challenge, the paper approximates the Kolmogorov complexity with the compressed size of the string achieved by a text compressor, following the established practice in algorithmic information theory. This approximation results in a fast-to-compute metric that effectively captures the complexity of the string based on the relationships between its characters.
Can you explain the main differences in the emergence of self-replicators between the BFF language and the fourth language experiments described in the paper?
The main difference in the emergence of self-replicators between the BFF language and the fourth language experiments lies in the structure and dynamics of the two languages. In the BFF language experiments, self-replicators primarily arise due to self-modification and interactions among different programs in a primordial soup setting. The BFF language is an esoteric programming language with a minimalistic design where programs modify themselves by copying from one head to another, leading to the emergence of self-replicators through simple operations like copying and overwriting neighboring programs. On the other hand, in the fourth language experiments, self-replicators emerge through a stack-based protocol for computation. Fourth variants differ from BFF by having a stack, allowing for operations that push values onto the stack or perform operations on the stack. Self-replicators in fourth experiments tend to consist of a long non-functional head followed by a short functional replicating tail. The fourth language exhibits more complex dynamics in the emergence of self-replicators, with self-replicators evolving to copy whole tapes and build upon existing self-replicators to achieve functionality. Overall, while both BFF and fourth languages lead to the emergence of self-replicators in computational substrates, the main difference lies in the mechanisms through which self-replicators arise. BFF relies on simple self-modification and interactions among programs, while fourth leverages stack-based operations and more complex program structures to facilitate the emergence of self-replicators with distinct characteristics.